Okay, so I'll begin right now, and if anybody else is joining, they can join during the course of the session. So yeah, mm, I'll share the screen. I hope the screen is visible to you. So yeah. So, welcome to another problem solving session for the course Geographic Information Systems. I'm Anchana, the teaching assistant, and the course instructor is Professor A.K. Saraf from IIT Roorkee. So, today we'll be discussing the digital elevation model part, that is predominantly of the week 8 lectures. But then, last session, I had excluded the last the last part of week 7, which was an introduction to the DEM. So I will be including that also, and the remaining part from the week 8 lectures. Okay, so yeah, before we get into the DEM part, we were like last session, we were just discussing about the map projection and different like projection systems and all. So I just wanted to briefly discuss about the Universal Transverse Mercator, or the UTM. Okay, so like this is just a brief introduction, not just introduction, just a trivia kind of thing. So you know what the Universal Transverse Mercator is. So this is basically a map coordinate system which divides the world into 60 north-south zones, each 6 degrees of longitude wide. So just a minute, let me just connect my tablet so that I can draw and show you. Okay, so what basically this universal transverse Mercator, what it does is that if we consider, like, let's say, of course, our Earth is not a proper sphere. Okay, so let's say it's not as wide like this, but still, yeah, just imagine that this is our Earth. So in this 3D model, that is basically what we are trying to do in map projection. We are just trying to make it into a 2D flat surface, right? So when we do that, when you have a UTM, so what you basically do is that this is a flat surface. You divide this into 60 zones. Okay, like, just a minute. So we have something like this, a rectangular sheet kind of thing. So we divide this into 60 north-south zones. So basically what it does is that we have this division, an imaginary division you can say. Then you have 60 such separation. And this is like, both for northern hemisphere, and both for the southern hemisphere. So like that we have 60 zones, and each of them the difference is 6 degree longitude, because we know that on the earth the vertical lines we call it as longitude, and the horizontal separation we call it as latitude. So each of 6 degree longitude wide, it is going to be separated. Now the zones are numbered consecutively beginning with zone 1, which includes the westernmost point of Alaska, and progress eastward to zone 19, which includes the main part of, I think it is a part of US. So that is just a trivia thing, just to make you understand. But the essence of this is that this coordinate system divides the globe or the world map into 60 north-south zones. And here we have XY, that is this northing, like the easting and the northing. So X basically talks about the easting, that is basically the latitude information, and the not the latitude. The easting tells you about the longitude, and the northing, the y coordinate, tells you about the latitude. So here you have a representation here. So if you have this point on the earth, just imagine like you have the UTM, you have this point. So basically what this, like if you get a representation like this, how we can deduce is that it is the zone 10S, that is zone number 10 in the southern hemisphere. And then we have this information over here, which is giving you the eastings and the northings information. So this is so this is 706, and then this is the distance from the nearest line, the vertical line, that is 832 meter east, that is like eastward direction. Okay, the direction is east. And then similarly in the north, we are looking at this direction also, and we are looking at this direction also. This is the x direction, this is the y direction, right? So this is the y information. So this gives you the x information, and this gives you the y information. So specifying a location means you will specify what zone it is, which it's already given here, 10S. Then you will talk about the easting and the northing coordinate in that plane. So about the x coordinate and the y coordinate. So that is just for information sake I mentioned. I don't think sir has given that much emphasis for UTM, but then it's something better to keep in mind, because the Mercator system, even the Google Maps also has used it. So for that purpose only I mentioned it. So yeah. Now the next one is a small video basically which I took from YouTube. You can also watch it there, but I thought it would be a bit informative for understanding like why we have a lot of map projections, and why all these, like you can't say any particular map projection is the absolute right one, because there is no map projection which is absolutely right. It's basically what you want. If you want a map projection which tells you the right direction, like the direction information is accurate, then you choose that one. And if you need a map projection which tells you the correct area of a country or whatever, like any feature on the surface, you have to choose that one. So the thing is, it's all about what information you need, and according to that you will have to choose the map projection like based on your need. Okay, so this is just a small video you can watch, and which might give you a visual understanding of why we have all these things. So I'll just play it. I hope it is audible to you.
All right, here we go. If I want to turn this globe into a flat map, I'm gonna have to cut it open.
I have also shared the link over here. So if you want, like I'll definitely share this PPT, but then if you want to see it again on YouTube or something, you can just go through it.
In order to get this globe to look anything close to a rectangle lying flat, I've had to cut it in several places. I've had to stretch it so that the countries are starting to look all wonky. And even still, it's almost impossible to get it to lay flat. And that right there is the eternal dilemma of map makers.
So here, this person is just showing you a visual representation of why we have so much of distortions in this flat representation of the globe. Like in maps, why it's not exactly as you see it on the Earth's surface. So what he is showing you is he's tearing apart a globe and he's trying to make it into a rectangular form, but which obviously we cannot do, right? It will be distorted. So in order to make it into a rectangular form, you will either have to stretch it, you will have to like do all kind of things in order to stretch it out into a rectangular form, which in turn results in changes in the orientation, changes in the shape and all those things. So that is what this person is just trying to show here.
The surface of a sphere cannot be represented as a plane without some form of distortion. That was mathematically proved by this guy a long time ago. Since around the 1500s, mathematicians have set about creating algorithms that would translate the globe into something flat. And to do this, they use a process called projection. Popular rectangular maps use a cylindrical projection. Imagine putting a theoretical cylinder over the globe and projecting each of the points of the sphere onto the cylinder surface. Unroll the cylinder and you have a flat rectangular map.
So this is what we discussed first in last class. I'm not letting it just play because you also need to understand what the person is trying to convey. So this we had discussed in the last class also. What we were saying was that if we consider the earth as a perfect sphere and you keep it inside a cylindrical material or something like that, such that the equatorial region is just tangent to the cylinder surface, then you project each of the point on the earth surface like this person just showed. So what happens is that the point closer to the cylinder will have less distance of projection, and the one that is a little farther away, that especially the polar regions, that will be like the basic thing is that the shape or size will not be very accurate.
But you could also project the globe onto other objects. And the math used by map makers to project the globe will affect the way the map looks once it's all flattened out. And here's the big problem. Every one of these projections comes with trade-offs in shape, distance, direction, and land area. Certain map projections can either be misleading or very helpful depending on what you're using them for. Here's an example. This map is called the Mercator projection. If you're American, you probably studied this map in school. It's also the projection that Google Maps uses. The Mercator projection is popular for a couple of reasons. First, it generally preserves the shape of countries. Brazil on the globe has the same shape as Brazil on the Mercator projection. But the original purpose of the Mercator projection was navigation. It preserves direction, which is a big deal if you're trying to navigate the ocean with only a compass. It was designed so that a line drawn between 2 points on the map would provide the exact angle to follow on a compass to travel between those 2 points. If we go back to the globe, you can see that this line is not the shortest route, but at least it provides a simple, reliable way to navigate across the ocean. Gerardus Mercator, who created the projection in the 16th century, was able to preserve direction by varying the distance between the latitude lines, and also making them straight, creating a grid of right angles. But that created some other problems. Where the Mercator fails is its representation of size. Look at the size of Africa as compared to Greenland. On the Mercator map, they look about the same size. But if you look at a globe for Greenland's true size, you'll see that it's way smaller than Africa, by a factor of 14, in fact. If we put a bunch of dots onto the globe that are all the same size, and then project that onto the Mercator map, we will end up with this. The circles retain their round shape, but are enlarged as they get closer to the poles.
So here, I just made a mistake earlier. This Mercator map projection that will preserve the shape, but it will not preserve the size. And especially such maps are used for direction purpose, like for navigation purposes. Because this map has been adjusted in such a way that whoever old times when in ship they used to use compass. Nowadays we have all these digital things, but in the past when it was completely relied on the map, so what they used to do is that line, if you had seen earlier, so they look at the angle between the line, if this is one line closer to it, they look at the angle and then accordingly they will navigate. So this one is mainly for the purpose of navigation, and also it preserves the shape of the countries or whatever is there, like continents. But then it does not preserve the size of the continents. That is what they were saying. Like you have the reason why that is so is because when you project, like we have this, okay, just, okay, so yeah. So as I was saying, so you have this earth as this, okay, my drawing is not so good, but anyway. So when you keep it in a cylinder, I don't know why it's not coming straight anyway. So when you're keeping this earth in a cylinder, like the sphere in a cylinder, and you're projecting it, so what happens is this polar region, this equatorial region is very much on the surface of that cylinder, right? So whatever like mm, country or continents, like their part is near that equatorial region or even the tropical region, that area is fine, like whichever is very close to the cylinder, that will be more or less very properly recorded in that projection. But then as you go away from the cylinder, so there some overestimation will happen. That is what this guy was also explaining. Like in this Mercator map, what happens is that like actually the African continent is really really big, but on the Mercator map, the African continent and the Greenland, they appear to be very similar in size. But the like yeah, size wise it looks similar, but in actual case what happens is this Greenland is very small when compared to the African continent. So that is what this person is trying to say. So if you take a look at this image that he has shown, so you can see that the equatorial region plus a little bit above and below that equatorial region, all that size and shape is preserved. So there you will not have that much problem. You can actually use the Mercator map even if you want to study something based on the size also, because equatorial region and regions very close to that is well accounted for in this Mercator map projection. But when you go to the polar side, like the North Pole and the South Pole, when you move much closer to those sites, uh, just a minute, I think I'll just share the screen once more. Probably it's not getting recorded properly. Just a minute. Just give me 2 minutes. I'm actually using two screens, so I think the screen that I'm actually recording on is not recording the presentation. Okay. Sorry for the interruption. I was actually using two screens, so there was some problem with the recording. Anyhow,
comes back to the globe, you can see that this line is not the shortest. Gerardus Mercator, 18th century, was able to the distance between the but that as compared to Greenland. But if we put a bunch of dots on, but are enlarged as they get.
okay, so this was the image that we were discussing. So only idea I just wanted to give was you can use the Mercator map mainly for the navigation purpose and for identifying the, like if you want the proper shape of each of the countries or continents. But then if you want to account for the size of each of the places, Only the reliable part is the region near the equator, both in the northward direction and the southern direction. But then as you go much closer to the poles in both directions, then the sizes are overestimated. Like it will be more than the actual size um, uh, on the globe.
Closer to the poles. One modern critique of this is that the distortion perpetuates imperialist attitude of European domination over the southern hemisphere.
Okay, the Mercator project the third world.
Projection. This displays land area. You can use the Gall-Peters projection. This is called an equal area map. Look at Greenland and Africa now. The size comparison is accurate, much better than the Mercator. But it's obvious now that the country shapes are totally distorted.
This is yet another projection, Gall-Peters. Just to understand how it is different from the Mercator's. So in Gall-Peters, that size difference that we saw in the Mercator map, that is accounted for. Like here, how he has shown you, the Greenland and an African size difference has been properly shown here.
Here are those dots again so that we can see how the projection preserves area while totally distorting shape. Something happened in the late 60s that would change the whole purpose of mapping and the way that we think about projections. Satellites orbiting our planet started sending location and navigation data to little receiver units all around the world.
Today, orbiting satellites of the Navy Navigation Satellite System provide round-the-clock, ultra-precise position fixes from space to units everywhere in any kind of weather.
This global positioning system wiped out the need for paper maps as a means of navigating both the sea and the sky. Map projection choices became less about navigational imperatives and more about aesthetic, design, and presentation. The Mercator projection, that once vital tool of pre-GPS navigation, was shunned by cartographers who now saw it as misleading. But even still, most web mapping tools like Google Maps use the Mercator. This is because the Mercator's ability to preserve shape and angles makes close-up views of cities more accurate. A 90-degree left turn on the map is a 90-degree left turn on the street that you're driving down. The distortion is minimal when you're close up. But on a world map scale, cartographers rarely use the Mercator. Most modern cartographers have settled on a variety of non-rectangular projections that split the difference between distorting either size or shape. In 1998, the National Geographic Society adopted the Winkle triple projection because of its pleasant balance between size and shape accuracy. But the fact remains that there's no right projection. Cartographers and mathematicians have created a huge library of available projections, each with a new perspective on the planet, and each useful for a different task. The best way to see the Earth is to look at a globe. But as long as we use flat maps, we'll have to deal with the trade-offs of projections. And just remember, there's no right answer.
Okay, so the gist of this showing this video was that we have several map projections, and we have to choose each of the map projection according to our need, and like each of them have like unique purpose. So it's not that one map projection is better than the other. So I saw it is an interesting video, that's why I just showed it here. So yeah, so that's all. Now we'll go to the digital elevation model part, which like it's the last part of week 7, and then week 8 also mostly like covers this digital elevation model. So you're already familiar with this term because sir had been using it on and off since the beginning of the course, GIS. Yeah. So as it is given here, like, you know, that name, digital elevation model. So it's not a real world representation, rather it is a model. Something is being modeled. Okay, so here it is a 3D representation of a terrain surface. Terrain is like the surface of the earth. Like we have certain specific definitions, but then for the time being, just understand that it is a 3D representation of any terrain surface, and mostly it is done for the earth, moon, Mars, asteroid, because like that, those are the surfaces that the humans have been able to explore so far. So we are more familiar with digital elevation models for the earth, moon, Mars, or asteroid, and as time comes, if we can explore other planets or other surfaces, then that also can, like, we can do the digital elevation model. So the digital elevation model, it represents the spatial distribution of elevation above some arbitrary datum in a landscape. So it's not like randomly you're saying, okay, like, because as you can see in the name itself, it is said like elevation. So elevation with respect to what? Like you cannot just say that, this like, you have a mountain like this, like this. So you need some point of reference, like, right? Like how much tall it is with respect to this surface. So most of the time it is done with respect to the mean sea level. Okay, the mean sea level. So from sea level, how high or how low a particular point is. So according to that, the digital elevation model is prepared. So some arbitrary datum in a landscape is needed. This datum, one common example is the mean sea level. They can also use something else according to the requirement, but then those parameters needs to be specified, like what we are using and why we are using it. So another thing that you have to keep in mind is, although the digital elevation model, it's predominantly used in order to understand the elevation differences in terrain, it can also be used to represent the groundwater levels, the chemical qualities of soils and water. Like that purpose of DEM has been expanded in such a way that it can also be used in such situations. So, and another thing which we have already discussed is that DEM is a raster representation of a continuous surface. So, we know that we have this raster data, we have the vector data. So, DEM is a raster representation of a continuous surface. It's usually referencing the surface of the earth. So, I think I have a, yeah, DEM model here. So, we have this black and white DEM model, and we also have the colored one over here. So this is the grayscale image, gray palette or grayscale image, and even the colored representation is also here. The basic thing is colors don't matter actually. What really matters is the cell value or value of the data, like whether even if it's a point, line, polygon, cell, pixel, whatever it is, only thing you have to be concerned about is the value of that data, like value of that cell value. Okay, so this basically is that like you need to assign such values for like for example, if it is the black and white image DEM model, so in that like how, like from white to different shades of gray to black, like you assign certain values and those values will represent this entire image. So similarly in case of colored also, so you are assigning those values and thereby are able to understand like what this image is trying to tell you. Okay, so it doesn't matter, like basically why sir had shown this image is to tell you that be it black and white, be it colored, that doesn't matter, but the cell values matter. Then sir had also discussed about the digital elevation model, the digital terrain model and the digital surface model. Like more or less he had tried to make a comparison out of it. So a DEM, as I said, is a representation of the elevation of the earth's surface above a certain datum in a digital form. So it's a model, right? So it's in digital form. Now this is achieved by taking elevation measurements at regular or irregular spaced points over the earth's surface. So that it's depending on the user. So either you can take it at regular points or you can take it at irregular spaced points, whatever it is. Anyway, it is something, a 3D representation you can say. Not 3D, like a digital representation of the elevation of the earth's surface. Now, in most cases, the DSM, so you have to remember what these acronyms mean. So this DEM you already know. Now DSM is the digital surface model and the DTM is the digital terrain model. Okay, so this is DSM and DTM, just to understand, like if I use DSM or DTM again, so it's so that you remember what it is. So in most cases the term DSM, it represents the earth's surface and includes all the objects on it. So that is like, even if it is natural or if it's man-made, whatever it is, in DSM, like you see all those things like plants, buildings, whatever it is, all those things will be represented in the digital surface model. But when you come to digital terrain model, it represents the bare ground surface without any objects. Like even if there is plant or buildings, it doesn't matter. It will only represent the bare ground surface. Which one? The DTM, digital terrain model. However, DSM will take into account all the other features like the vegetation, natural features, anything. Even the built features also it will take into account. So most of the time this is not like, they don't use DEM, DTM, DSM separately. Like DEM is often used as a generic term for DSMs and DTMs, like a more generalized one, like everything is accounted for in DEM, that kind of thing. But it only, and not everything, like it only represent height information without any further definition about the surface. So if you have something which is giving you the information about the natural or built features, then we specifically say DSM. But more or less, we when you say DSM or DTM, generally people just say it is like it is a digital elevation model. You just have to be familiar with these terms. Like if you get some question related to this, so you know like what is. Then Sir had discussed the various techniques to generate digital elevation models. So the most preferred method for generating digital elevation model is the remote sensing one. Like whatever information you are getting from remote sensing, it can be aerial photographs, it can be satellite images, whatever it is. Even the drone images, all those things can be used in order to generate the DEMs. Okay. So the DMs can be generated using the following methods. It can be used like prepared using survey topo sheets like contours, point, heights, all those things, which is basically done using spatial interpolation techniques. So spatial interpolation we had already discussed, but we'll discuss it again. So that is like a very basic thing without using much of the like latest technology. You are basically just using certain information and then preparing the DEM model. Then you have the stereo pairs like using spot or cartosat, like those are satellites. Okay, spot, cartosat, these are satellites. So you use the data sets in order to generate a DEM image. This is a remote sensing method. Then we have the thermal infrared data of a hilly terrain, which is also a remote sensing method. Then we have radar data pairs. Basically, apart from this topo sheet, we use a lot of satellite methods, like different remote sensing methods in order to generate the digital elevation models. So first thing that we are going to discuss, okay, before getting on to that, yeah, we'll just discuss this image that Sir had given. Like the first point, right? The using the survey topo sheets. So you have a topographic map which is on a paper, right? So that's the most popular way when how you find the topographic map. Even if you just Google search for topographic map, I think you might get a scanned version of that rather than a digitized version. So it's mostly on paper. Okay. So what we do is that we scan this topographic map, then you get a image of that, right? That image we will do the georeferencing, which has been discussed in the previous sessions. So georeferencing is basically you will find some common points that you can see on the scanned copy and an actual georeferenced map like the Google map or something like that. So what you do is you establish some ground control points, like same points that you can see on this map and also on the Google map or something else, some reference map which is already georeferenced. So you find those ground control points, you input the lat long information, and then thereby you can georeference this topographic map on any of the GIS softwares like ArcGIS or QGIS. You can do that. So thereby you get a georeferenced digitized image of that topographic map. And then basically you also add in this ground survey, like some points, some sample elevation sites or lines, some contour lines, all those things you can just add. And you may not have the entire information, right? Like you may just have a few point information or few line information. So what you do is, with the available data, like with this sample data, we will do the interpolation. Like we will increase this point data or the line data by doing the interpolation, like using the sampling, like the sample sites. And then finally the output is a digital elevation model. So this is just to say how, like why we are including the interpolation. Okay. So first one, as I said, is spatial interpolation, which is done on the topographic maps or topo sheets. So spatial interpolation is a procedure of estimating the value of properties at unsampled sites within the area covered by existing observations. So if you remember, I had also mentioned this in previous sessions, like you have an area, let's say this is an area, I'm just randomly representing it, and you have some kind of information from this, like let's say I had given the example of rain data, so we can just say rain data. Okay, so we have rain data we need to get it for this entire area, but then it's a very huge area and it's not possible to get the information on every little point on this area. So what we do is we strategically choose certain points, and then accordingly, like just some random points, but it's better if you can choose it strategically, so that you can just estimate the value of nearby areas using these sample sites. Okay, that is known as spatial interpolation. So this basically predicts values for cells in a raster from a limited number of sample data points. So if you have just, let's say, 8 sample data points, you can actually predict values for remaining all cells using just these number of points. And it's always better that you have a little, it should not be like you have 2 points and you use that to interpolate. So some like permissible number of points are needed. It's not necessary that you have to have like 80% or something like that, but some number of points are needed in order to find the value of properties of the unsampled sites. Now this is used to predict unknown values of any geographic point. It can be elevation, it can be rainfall, chemical concentration, noise levels, etc. So the basic idea behind spatial interpolation is that observation is the observation that points which are close together in space are more likely to have similar values than points which are far apart. This, if you remember, we had already discussed. It is the Tobler's law of geography. So it's like basically whatever point is nearby, and if you have information about one point, then it's a observation that has been made that the point next to this point will have similar values. So accordingly, we predict the unknown values. So here this was an example which we previously showed also, but again, if you take a look at this, here we have 7 points, 1, 2, 3, 4, 5, 6, 7. Okay, we have 7 points, and all these points are having some values also, like here 14, 24, 30, 27, like that. Okay, now just assume that these are elevation values. Okay, so implying these points and using spatial interpolation techniques, we generate a surface which is somewhat like this grid that you can see here. So in between, like let's say for point 16, if you take a look at this, so that point 16, a cell has been created. Okay, And not only has it created a 16 cell, you already have a 14 over here. Then you have a 24 over here, you have a 20 over here. Then this 20, 27 and 30. Okay, so you have 1, 2, 3, 4, 5, 6, 7. 7 points in this grid, and the remaining points are obtained by spatial interpolation. So because of this spatial interpolation only, we are able to fill these regions. Otherwise, we have no other idea like what elevation that region has. But because we can do spatial interpolation, we get the values of all these regions. Now the problems with interpolation, like we do interpolation, like the main problem with that is the accuracy. Like we are doing it, but then at times our assumption may not be right also, right? Like just because our like Tobler's law of geography is there, that is an observation also, but it's not necessary that all the time it can be true. Like sometimes, let's say for elevation purpose itself, like this mountain, uh, like the elevation is like this. I'm just giving a very simple example, and the nearby mountain is even more taller or something like that, but then you don't have the details of this part, or like, yeah. So if according to this law of Tobler, like if we use that, according to that we will be expecting an elevation in this point, like to this point, but then actually it is even more bigger. So such accuracy problems can come. Visual representation or visual checking is also possible, and at times like that edge effect can also be a problem. Like at times you may not have the exact data along the margins, so they might just make a random interpolation which may not be true. So such problems are there, but if your requirement is not so specific, like you don't have to have that much of details, you just need to have an overview, then this is more than enough. Like doing the interpolation is more than enough. So then another one that sir had discussed, like another method or technique for digital elevation model is the DEM generation from stereo pairs of satellite images. Just a minute. Okay, so optical remote sensing images such as those acquired by satellites are conventionally used in generating DEMS using the photogrammetric technique. So we have this images that are taken by satellites. So what like remote sensing images are there acquired by satellites. So what we use is we use these images in order to generate the DEMs or digital elevation models. So what it basically does, like what the stereo pairs means is that the satellite that's basically the same location image, like a pairs of images which are taken from slightly different angles. So when the angles are different, you can actually understand where some elevation might be there or some depression might be there. Because if you just take an overhead image, then you will not understand if that region is elevated or has some kind of depression. But then if you take it at some angle, and that too you have a pair of images accounting for that, then you can actually use that in photogrammetry or topographic mapping or whatever it is, and even for DEM generation. So what it essentially means is the photogrammetry is the like it's extraction of 3D measurements and models from photographs. That is all. Because the photograph that you take, like if you take a photo of, let's say, you just step outside and you are taking a photo with your phone. Okay, if you're just taking an overhead image, like just let's say you have an image, like you have a surface over here, okay, undulated surface. Now, if I take an image from this point, just directly above it, I will not be able to understand that, okay, this point is above and this above or like higher than this point, right? That is not possible from an overhead image. But if I take an image from this side, or from the other side, then I understand that, okay, this region is not flat, rather it has some kind of elevation. So that way, like you can actually use stereo pairs in order to generate the digital elevation models. So here sir has given the examples also of the different satellites that has been used. So here we have spot satellites imaging instruments are fitted with a steerable mirror which enables the instrument to image areas up to 27 east or west. Like basically all these satellite images can be used in order to generate the DEM model. So this example, like as that has been given here, each day it has been collecting the image, it seems. Okay, so like day 0 it took one image, on day 5 like same location but on different days it has been taking an image. So this is -5. So before day 0, 5 days before the day they started it, like making the like taking the information, and then up to say like 10 days or something like that. So if you have multiple coverages of the same area and at different angles, then you can actually generate good stereo pairs. It's not just with 2 images, but if you have multiple images, it's more easier. And once we have them without any cloud cover, that is also important, because satellite images, like if you have used these satellite images on, like if you have searched for them on like USGS Earth Explorer or some other sites, then you have this option to choose the images without cloud cover, because if cloud cover is there, then you are not actually able to see the surface properly, right? It is like, it's like you have some blanket over the region. So if you have good stereo pairs with no cloud cover or something, then it's much easier to generate the digital elevation model. So if you have a digital elevation model, and if it is possible, you can actually put a satellite image over it and get a proper 3D perspective, which will give you a good feeling about that area. So here sir has also given an example of the Cartosat. This is Cartosat 1 data of a 2.5 meter resolution, I think. And this panaft, that is panchromatic image, okay? Like this is a colored image on the left, and the other one, this one, is a panchromatic or like black and white image kind of thing. This is for the same area that was generated. So here, like you can actually differentiate with the colors and everything. Here it's not as possible, but then still some undulations and everything, you can just make it out. For example, this is like a valley kind of thing that you can see here also, but it's easily deducible in this image when compared to this one. So what you have to keep in mind is that one powerful technique for generating digital elevation model is interferometric synthetic aperture radar, where two passes of a radar satellite like the RadarSat, TerraSAR, NVSat, Sentinel, whatever it is, or a single pass if the satellite is equipped with two antennas like the SRTM, which I have written here, collect sufficient data to generate a digital elevation map tens of kilometers on a side with a resolution of around 10 meters. So it's like with advancement in technology, the satellite, their resolution has increased, the area that they can cover with as much good clarity as possible, all that has increased. So, like the quality of digital elevation models has also changed. So here I had selected only few slides from whatever sir has discussed because there were plenty and we won't have that much time for it. So whatever I felt was worth this, like not worth, like which needed a little bit of discussion, only those I have taken here. So here you can see a terrain with a multiple spatial resolution like DEM model of the same area. So this is from a different DEMs of the part of Kutch, Gujarat, like same area but different DEMs. So here you have the SRTM. So okay, I forgot to discuss the SRTM. So the shuttle radar topography mission, that is the SRTM, it collected the topographic data over nearly 80% of the Earth's land surface, which is like almost it has accounted for all the major portion. So that is the first ever near global dataset of land elevations. Okay, like that's what I was trying to say. Like earlier, it was not possible to cover that much area or with that much quality, but now we have the technology for that. So the payload consisted of two radar antennas. Two antennas are there. That's what I was saying. Like either if only one antenna like is there, then it will have to go twice. Two passes needs to be done in the same area. But if you have two radar antennas, then it's easier to collect the data with one pass. That pass is basically at that how much times it has to capture that area. So this radar antenna, one is located in the shuttle's payload bay and the other is installed on the end of the of a 200-foot mast that extended from the payload bay. It's basically at two different positions you have antennas and that is going to receive the signal. Now each SRTM radar assembly, it contains two types of antenna panels. You have C band and the X band. This is not required, this is just information. Just have, like if you are interested to know about SRTM, that's why I just kept it here. Anyway, the C band radar data were used to create near global topographic maps of the earth called the digital elevation models. So it was this C band data which was used for creating this global DEMS, and the data from X band were used to create slightly higher resolution DEM, but not like the thing is C band is permitting you to collect the like enabling you to get the information for on a global scale, but X band, it is more or less like resolution wise it's higher, but not the global coverage like C band. The two radar datasets were combined to create interferogrammatic maps of scanned areas. Interferogrammatic means basically if you have two images, obviously there will be some differences, right? So we make such idea of such differences in order to make the digital elevation model. Okay, so then coming on to this image, so as I was saying, it is the different DEM of part of Kutch, like same place but different DEMs in Gujarat. So here we have a SRTM 90-meter resolution. Then we have SRTM 30-meter resolution. So here you can see it's a little farther, and then the other one is a little more closer image, right? A little more zoomed in kind of thing. Then we have Aster 30-meter, and then we have the Allos Pulsar 12.5 meter. So here, as the this number like from 90 to 12.5, as it reduces, the more details you can see, right? So if there is a requirement, only then should you go for higher spatial resolution, even for like when you're looking at satellite images or the digital elevation models. If you don't need that much of details, like you just need just an overview, then the only thing that you have to go for is a lesser resolution image. But if you need more information about a very small area, then you have to go for the higher resolution image. So most of the time people go for the 30-meter resolution. That's a general thing. But because in 30-meter, various choices are available. But if you go for higher resolution, the cost will also increase, and like if it's not useful, then there is no point. Most of the free satellite image data that is of 30-meter resolution. Then Sir discussed about the light detection and ranging. So this is basically LIDAR, okay? That is a remote sensing method which uses light in the form of a pulsed laser to measure ranges to the earth, like variable distances. So like how you have this laser pen. So with that pen, like it's something like that. It's basically it uses some light in order to understand the difference distances to the earth from different points. Okay. So this, what you have to understand is that if you have a satellite or something in the outer space and you need to determine the distance on the earth surface, like some point on the earth surface, it's not possible to measure it manually, like using some measuring instrument scale or anything. So for that purpose we use light. That is what LIDAR does. This has been introduced like some like a little less than a decade back. So when these light pulses are combined with other data record by some airborne system, it generates precise three-dimensional information about the shape of the earth and its surface characteristics. So more the information that you get, the better it is to get a very detailed image. Topographic LIDAR typically uses a near-infrared laser to map the land. So these are different techniques that have been used in order to generate a DEM image. So we are just discussing that, but the basic general idea that you have to keep in mind is the techniques that we use mostly nowadays is the remote sensing methods rather than the spatial interpolation methods. We use it, but it's not as frequently used. So here we have a LIDAR data collected by air. This is by NOAA survey aircraft over the Bixby Bridge in California. So here LIDAR data reveals a top down like here, okay, and profile views of Bixby Bridge. Like this is the top down view from the top. Okay, so you basically understand there is something over here, right? And this shape that you see here, like there is a narrow path. That narrow path you can see, and also you can see that this is a kind of a valley kind of thing. Okay, so that top view is also there, the profile view is also there. So essentially LIDAR will provide the opportunity to make high quality elevation models of two distinct types: first return and ground. So a first return surface includes tree canopy and buildings and is often referred to as the digital surface model that we discussed. Okay, that is the first information that you're getting. So it will include all the trees and whatever it is, buildings are there, anything, it will account for that. So you get basically a digital surface model. The ground model or the bare earth contains only the topography and is frequently called as the digital elevation model. So you can actually make these two models, the first return and the ground. First return is basically referred to as the DSM, the digital surface model, and the ground model is basically the DEM model. So if you take a look at this image, here you can see, right? You can see the tree line over here, you can see the buildings over here. So that is represented in the DSM, but when you look at the DEM, you don't see all those things, but you do see how the surface is, like where elevation is there, where depression is there, that things are seen in the DEM model. Because at times that is all that you need. Okay, you don't need information about what kind of trees, not what kind of tree, like how far the tree canopy is present. Sometimes you don't need it. If you need it, of course you have to make use of the digital surface model, but if you don't, then always go for the DEM model. That's why sir has also been emphasizing that it is always user defined, like what the user needs, according to that you will collect the data and do the modeling. Okay, not the problems, but basically I have to discuss the other two lectures, but I couldn't include that in the PPT. So I will show sir's presentation and then we'll discuss along with that. Okay, so I'm sorry I couldn't include that, like there was a lot, like I couldn't go through the entire part, so we will discuss it using this. Okay, so as we were saying, so the digital DEMS can be generated using all these methods. So we have discussed the previous ones. So in this, we will be discussing the thermal infrared data of a hilly terrain using the remote sensing method. So this NOAA AVHRR data, this is basically satellites, okay, NOAA AVHRR data for DEM generation. So the general assumption is that temperature and elevation are inversely related. So here this AVHRR is a very high resolution radiometer and it has high, like as the names, as I said, it has high resolution. So this relationship can be exploited, that is the temperature and elevation are inversely related. That can be basically exploited for this generating this DEM models. What I understand from this is that if you have a region, I'll just draw it and show you. I don't think I can draw it here. Okay, there will be some problem because last time also I tried. Anyway, like the idea is that okay, I don't think I can draw it here, but the basic idea is that the temperature will decrease with elevation. So that is like you know, right, if you look at the mountains and all, like if you are going to some hill station or if you have seen the like the Himalayan ranges, so as you go up the temperature will go down. So you can use certain satellites which you know, understands the thermal data and all those things, and then based on that you can actually understand, like if like the temperature data of a particular area is shown as very cool, then probably that is the elevated area, and relative to that the other area is less elevated, that kind of idea. I don't think we need to. Here sir has given the data specification, so this actually you can go through, like this is basically whenever you have some kind of satellite image or anything, so we need to understand all these information, like what kind of sensor has been used, how many channels, altitude, at what altitude the image has been taken, the temporal resolution, like how many images has been taken in a particular day. So all that kind of information is needed in order to actually process a particular satellite image. Only then will you understand, okay, what kind of information that image is giving you. So the spatial resolution, here you can see it's about like 1 kilometer for this NOAA AVHRR, and that's like 1000 meters. Okay. And then the temporal resolution, because the different types of resolution will be discussed, I think. So temporal resolution is how many images can be taken in a day, like number of images in a particular time period, or in a second, or whatever, that 1 hour or 1 day or whatever it is, in that time period how many images can be taken. That is telling you about the temporal resolution of a satellite. Then radiometric is like how many like how do I say, radiometric resolution, like if you have so many grids or cells, the more high resolution the image will be, and if not, it will be a little more coarser, like information will be less. So what essentially they do is that it depends on where the place is located, and even at times what can be done is the same area can be visited once a day, or it can also be visited in a daytime and the nighttime. This is just to show you the methodology. I think I would discuss this part better maybe in the next class, because sir has given you a lot of images and I've not gone through all of them. Maybe this one we'll discuss in the next session, so I can also include some more information in this. So we can actually go to the resolution part. Sir has mostly used a lot of images in the previous one, so it's a little difficult for me also. I'll discuss it in the next class. Okay, so we'll go to the different resolution, like digital elevation models and different types of resolution. So as you know, digital elevation models, like we discussed, it's a storehouse of information, and a lot of things can be done with the DEMS, right? So you need to understand what kind of information and how much of information do you require. So for that purpose, we need to understand what a resolution is. Okay. Okay, so the first one is the spatial resolution. So that is the measure of how closely pixels can be resolved in an image is called the spatial resolution. And it depends on the properties of the system creating the image. For practical purposes, the clarity of the image is decided by its spatial resolution. So in case of satellite images, we need to see how the pixels are resolved. Okay, so if you have something like you know, it's very difficult without drawing, but anyway. Basically what I'm trying to say is, if you have a square, or else one thing I'll do, I'll open a blank page here so I can show it also. Okay. So what I'm trying to say is, if you have a image like this, let's say, okay, now if you have a very coarsely spaced cells, like pixels are like very far apart or something like that, then that resolution is not so good. Like it only gives you a coarser idea, nothing much detail about that particular area. But if your resolution is somewhat high, then it will have closely spaced pixels. Like this. So this will have more information, because in this case, like let's say this big square is basically, it has been divided into 4 squares, or maybe let's say 9 squares or something like that. So that much of additional information has been included in this particular image. So in remote sensing, resolution means the resolving power. So whenever you buy a phone or something, so then also you look at the resolution, right? How much like higher the resolution, better image you get. So it's the capability to identify the presence of two objects, and also the properties of those two objects. So like if you have a very um, less resolution image, you will not be able to differentiate the features on that image. But as the resolving power increases, you will be able to understand that, okay, there are two different things here instead of one. So a DEM that shows finer details is said to be a finer resolution compared to the DEM that shows coarser details. So we have these terms over here, which is known as horizontal resolution and vertical resolution. So horizontal resolution is which is the spatial frequency at which samples are taken or modeled. The cell size in x and y directions, those usually being equal, and the cell being always square. Whereas in vertical resolution, in a DEM, which refers to how frequently DEM can record a difference in elevation, often this is in integer meters or feet. It's basically what they're trying to say is, if you remember, we had also discussed this regarding cells and grids. Like in cells, we are more or less like interested in knowing the horizontal expansion of whatever image is there, whatever information is there. But and more or less each cell will be in the square shape, and we don't it's mostly positive numbers, positive integers, and nothing else. But in case of DEM, in this vertical resolution, we will consider the positive, like the values of that grid can be positive, negative, or like it can be both, okay, positive or negative, because here elevation is taken into consideration. So from a particular surface, how high that particular area is, or how low that particular area is, that is taken into account. So what happens is that if you have a grid like this, a cell, something like this, a raster image, so in that, if it's a and if it's a normal image, here the numbers will always be positive integers. It can be 2, 5, something like that, 10 something. But if suppose this is a DEM image, a grid image, in that case this can even be -5, which tells you that, okay, this region is below a particular datum. Vertical resolution is often higher than the horizontal resolution, because there we are taking into account more details, not just how in horizontal manner how things are distributed, but rather we also know how high or how low a particular region is. The DEM spatial resolution alone does not determine the accuracy. So what accuracy means is like you might be familiar if you have some exposure to statistics. So we have this terms accuracy and precision. So accuracy is a statistical concept which states that likelihood or probability that a particular set of measurements are within certain range of the true value. So it's like how I can show you an image, like I can draw and show you. And this is a very common image that is used in order to uh, talk about accuracy and precision. Okay, so we have these dart boards, right, where we throw an arrow or something. So our idea is that we need to throw an arrow at this point. Okay, so we have a like somebody threw it and we are getting the points like this. Like it's very randomly distributed. So in this case, the accuracy and precision are both low. Okay, this has low accuracy and low precision. So that is because our intention is to get this area, but the other points, like all the points are like sort of scattered, so it's basically not anywhere near the accurate or the true value. So that is what accuracy is. It's a statistical concept which states the likelihood or probability that a particular set of measurements are within certain range of the true value. Here the true value will be when all these points are at the center, but it is not. So here accuracy is low, precision is low, because precision, it is a statement of the smallest unit of measurement to which data can be recorded. Like when you say like when you're copying something, some image or something, we say it's very precise, like to how fine detail you can actually match it with the original one. That is what precision is. So here low accuracy, low precision. Then I will draw another image, and okay, my drawings are not at all good, but still. So here all these points, instead of being spread out, they are in one place. But here what you have to understand is this center portion is where we are aiming at. Okay. So in this image, it does not have any accuracy because we didn't get any point in the center part. So this has low accuracy. This is to understand, like make you understand the difference between accuracy and precision. It's a more visual idea to understand how different they are, rather than making it all about a definition. So yeah, so this has low accuracy, but it has high precision because all the points are in one area. It's not very spread out. So it has high precision. So precision is never related directly to the true value. It is more how intricate the details are. That's it. Okay. So this is another one. And then you have another image like this, in which you have points in and around the true value. So in comparison to the previous ones, here you have high accuracy. Accuracy is high, but since they are very spread out over here, unlike this, the precision is low. Low precision. Okay. And then final image where you have both accuracy and precision high, that is this one. So both are high. High accuracy and high precision. So a very simple idea is accuracy is how close a measured value is to the actual value, and precision is how close the measured values are to each other. That's very much clear from here, right? Like here both accuracy and precision are low because all the points are very much spread out and none of the points are near the true value. So both are low. But here the precision was high because all these measured values, although they were not like close to the true value, but then they were close to each other. So we say it is precision is high. So finer resolution DEMS may offer greater precision, although not necessarily greater accuracy. Like finer resolution DEMS means the ones with a lot of information. So information will be there, that which means precision is there, but it may not be accurate. Like it may not be representative of the true thing. So for example, you may have a sensor with a 10-meter spatial resolution, but if it suffers from some kind of errors like systematic bias, noise, or something like some problem because of the angle at which that image was taken or the time at which it was taken, some problem may be there. So it will not be accurate. It may not be accurate, but it will be precise. Like whatever is there is represented, but certain parameters may not be correct. So here you have a very good image which shows you things about high resolution and low resolution. So the first cell, if you can see, these are simulations, okay? So 110 by 110 kilometer cells are there, and as you can see, it is completely like very blocky appearances there, right? We are not able to understand anything. Like sometimes if you zoom in an image which was taken in a very low resolution camera, then you can see this pixelated kind of thing. You won't understand anything. It's all just colors. So it's not very easy to resolve also to pixels or cells that easily. Now if we go to a better side of spatial resolution like 30 by 30 instead of 110 by 110, then like we see some pattern, something is there, like it shows some kind of difference, but even then it's not very clear. But if you go to this 1 by 1, this is a 1 into 1 representation, we get the pattern very easily. Like we understand what is shown here, and this is the expected precipitation patterns. So when we move from the coarser resolution to the higher spatial resolution, like from here to here, left to right, it is more comfortable for us to resolve between the cells. Compared to this image, the rightmost image, you can see the middle image is a little more, like you can differentiate between the cells, but then it's much better in this one. Easier to make some sort of interpretation. So another example is the one that is given below. So here we have a 1 by 1 matrix, okay? So that's like just a single cell is there. So nothing, no information can be made out of this. You just see this plain color, okay? This is the unit cell. So that's a single cell representative of whatever that image is. Only one cell is shown here. Now when you do 2 by 2, so you have 2 cells in one row and 2 cells in one column also. So some more information has come, like the cell number has increased. Now I think this is 5 by 5. Yeah. So some more information. So as you increased the number of cells or pixels, whatever it is, now you can see when you go to 100 by 100, you see actually what that image was, which is basically this R written here. But in the 1 by 1, you might have just seen one single cell somewhere over here or somewhere where this plain color is there. So that is how the resolution varies. So very fine details you can have in your mobile phones also, like the digital cameras that you have, you can go from 5 megapixels to 10 or even higher. Like nowadays it's really high, right? 50 megapixel, like all those ranges are there. So very fine details we can get, and that way we can understand things much better. Earlier we needed to have like digital cameras on hand in order to get a better image than the phones, but nowadays even the phones are more than enough to get a good quality image. Then sir had given an example where we are comparing small versus large cell sizes, and here we have a polygon. Okay, this is just a polygon, nothing, no cells are there, but then you make it into a raster image. Okay, polygon is converted to raster, and here we have a 16 by 16 cell. So here we can see a boundary which is very much similar to the actual polygon, but as the cell number decreases, it does not conform to that boundary that very, like, in a good way. So smaller cell size will give you higher resolution, like it actually represents the polygon that has been given here. Higher feature spatial accuracy, but this will take time to display because it's including a lot of cell information, like cell values are there. So it will take time to display, process, and the file size will also be large. So you will only go for this high resolution ones or finer resolution ones only if you need that, because it's going to be time consuming and space consuming. So when you go for, like, if you don't need that much of information and it's not as needed, then go for the coarser resolution or less resolution one, which has larger cell size, lower resolution, lower feature spatial accuracy, but it is faster to display, faster to process, and file size will be small. So it's always dependent on the user. So here also you can see, right? When cell is very small, then you have higher spatial resolution. And when cell size is larger, like here, the 8-meter one. So you have coarser spatial resolution. You don't see much details here. But as you go to 1 meter, you see more details. Like 1 meter resolution means it's taking every information in a, like, 1 meter scale. Here it's at 8 meters, so the information amount is less. And here you can see, right, the cell size has also decreased. So the first 8-meter one, if you see, it's actually just giving you a very coarse information about this entire region, and then as you come to 1 meter, it's giving you a point information. The same thing, like effect of increased data resolution with scale constant. So here scale has been kept constant, 1:20,000, but the cell size has varied. Here the cell size is 15 meter, so not much information is available. But when the cell size was increased to decreased to 15.24 centimeter, then all the details can be seen here. So scale is intact, that is the area that you're covering is the same, but then cell size has changed. Now here cell size is same, but scale has been changed. So what the thing is, cell size is intact, but you have zoomed in. You have gone in much in detail. So scale has decreased. The increasing with a constant spatial resolution. So here it is 1:50,000. So a lot of information is here. This is a large scale image. And then when you zoom in, this is like, no, this is a large scale image and this is a small scale image. This DEM things have already been discussed, so I don't think that is needed. Anyway, there are different types of resolutions. So we have spatial resolution, spectral resolution, temporal resolution, and radiometric resolution. So these are different resolutions that are used in remote sensing. So spatial resolution, like I showed the examples also, it is the ability to distinguish closed space object on an image, based on the cell sizes or grid sizes, whatever it is. Spectral resolution is the location, width, and sensitivity of chosen wavelength bands. Um, like hyperspectral image are there, multispectral image are there. So, like that, you have to go into much details in order to understand this, but um, it's basically the how far that each wavelength is being considered. Temporal resolution is time between observation. It can be between days, hours, even if you as smaller as you bring it, the more costlier it is going to get. So how much time? Like if I am taking an image of an area in one a particular day at a particular time, and I'm taking that image in the next day at the same place the next day, then the temporal resolution is for 1 day. But if that same place I'm taking it 1 hour later, temporal resolution will be 1 hour. So like that. Radiometric resolution tells you the precision of the observations. It will not tell you about the accuracy. It may not be very true to the actual value, but it will give you a precision regarding the observations. So, okay, this is not. And this image also, sir, has shown you for spatial resolution, ability to separate objects in X and Y. We have already shown that. This and all, I don't know if it's needed. This is regarding the instantaneous field of view which is used in remote sensing. So this is basically like if you have an aeroplane or something like that, and you have some kind of sensor attached at the bottom which is trying to take an image, some camera or something. So the instantaneous field of view is an angular cone like this area. Okay, so we'll measure this angle, and that way we know the resolution, like how much that area has been covered, what area has been covered. Such details are given here, but I don't know if this is necessary. So ground resolution element is calculated by this IFOV, which is this angular this part, into the height, at what height it has been taken, and the instantaneous field of view angle. That will give you the ground resolution element. The problem with spatial resolution concept is that unless we don't know the height, IFOV is going to change. Like if it's closer, IFOV might be a little more. If it's at a height, those things can change. So we need to specify at what height that satellite or the flight has been flying, from what height it has taken that image. And the lens also, here you can see, right, wide angle lens means more area is covered, standard lens means the area less, and telephoto lens means it's more intricate, like it takes into account more details, so it is much smaller. Okay, I don't think this is required here, so we'll go to the few problems that I have kept. I had compared your week 8 assignment and the problems I had. So I only had like 3 questions which were not similar. So I'm just discussing that. And once the solution for week 8 is out, we'll discuss that in the next session. So this is the first question. Generally, which digital elevation model is more suitable for highly rugged terrain? This is regarding the satellite data which we discussed, and it's more of a general thing. Okay, I had not seen Rahul's message earlier and I don't think he's here. Maybe in next class I can tell about this. Okay, so the answer to this question is Aster GDEM, 30-meter resolution. That is mostly used in order to get a idea, like DEM image for a highly rugged terrain. One powerful technique for generating digital elevation models is interferometric synthetic aperture radar, where a minimum dash number of passes of a radar satellite are required. This I had mentioned. Of course, it depends on the antennas that are present, but then generally you need at least that number of pass in order to get a proper DEM. The answer is 2 passes. At least twice you have to cover that area. If it's more, it's okay, but that's, of course, it's always dependent on the cost, right? So at least minimum 2 passes needs to be done in order to get a good digital elevation model. Dash is a statement of the smallest unit of measurement to which data can be recorded. This we had just discussed. Of course, I have not specifically told about this definition, but it's what we had discussed. The answer is precision. Okay, that is the smallest unit to which a measurement can be made, but it need not be very correct because of some systematic errors with the data collection or something like that. Okay, so that's all that I have. Only 3 problems were there, but that's because the remaining questions that I had, it is similar to the one that you have for your assignment, and I'm not supposed to discuss that one at least until your assignment solution is released. So that's why I've not mentioned it here. So if you have any suggestions, like some topic suggestion or something, you can mention that. And the last 2 slides that I had discussed using the PDF, like I couldn't prepare that into the PPT. So probably the important points maybe I'll again discuss in the next session so that it's easier to understand. There were a lot of images, so it takes a little time for me to compile it also. Okay, so if you don't have any further questions, then we can end today's meeting. Thank you so much for listening patiently.